Okay, so this is part 2 of 2 for creating priority lists. In the first video, we looked at the decreasing time algorithm, and in this video, we're going to look at the critical time algorithm. So as you recall, this slide was in the last presentation, and we had gone over these first two. Should we complete tasks in alphabetical order? Should we complete tasks based on how long they take to complete? Those were covered in the last video, part 1 of 2. And in this one, we want to focus on should we complete tasks based on the preceding tasks they have. So, schedule tasks based on preceding tasks. As we said in the previous lesson, we talked about the decreasing time algorithm, and we created our priority list by scheduling the tasks that take the most time first, and then continuing in descending order of task times. So now we're saying, what if delays are caused by preceding tasks instead of just the longest tasks? So we say, what if we did our scheduling um, instead of on individual task time, we based it on combined task times. So the idea behind this is there's a chain reaction if preceding tasks aren't done to get the tasks that have the longest processing time um, to the workers as soon as possible, then when we do get to that task that has a lot of time, it's going to delay the project finishing time. So if we look at this graph, we want to start this conversation of critical time by looking at something called the critical path. The critical path from any vertex to the end vertex is the path that has the greatest weight. So if we look at this one here, if we look at vertex G, we see that vertex G has two different paths to get to the end vertex. We have this first path up here, and then we have a second path down here. So we want to look at the path that has the most weight. So we're going to find the critical path for G, E, and H. And if we look at G, we can go the path from G to D to A to the end vertex. And if we add up all of the numbers there, G has a time of 2, D has a time of 7, A has a time of 2. This path to get to the end would take 11 units of time. And then we noted that G also has a second path. We can go from G, but instead we can head towards vertex E, and then to B, and then to end. And if we added up these times, we would have 2 units of time for G, 5 units of time for E, 3 units of time for B, and that gives us 10. Now, the goal of the critical path and the critical time algorithm is to identify the path with the most weight, because that means the most time to get to the end. And what we're looking for is a chain reaction of events that are going to cause delays in our scheduling. And that's why we're always looking for the biggest number. So the critical path for G is G, D, A, end. And this number 11 is known as the critical time for G. And you're going to see that we're going to start denoting critical time in these graphs by using a square bracket and the critical time. That means the time of the longest path. So let's look at this now for vertex E. And if we look at vertex E, we see that there's only one path. We go from E to B to end. So there's not much to do here. We just say, all right, the critical path for E is E to B to end. And if we add those up, we see, well, end takes 0 time. We can put that end has a critical time of 0. And if we add 0, 3, and 5, we get a critical time of 8 for vertex E. And the last one in this slide is to look at vertex H. H we see has two different paths. I can go from H to E, from E to B, and then from B to end. And if we add up each of these times, H is 1, E is 5, B is 3, and end is 0. So 1 plus 5 is 6, plus 3 is 9, plus 0 is 9. And now we want to consider the other path from H to F, H to F, from F to C, and then from C to end. So we see that there were two different paths that we can take from H to end. And now we want to add up their times. H was 1, F was 3, C was 4, end is 0. 1 plus 3 plus 4 plus 0 is 8. We want the larger number because we're looking for what could possibly delay our project. So H has a critical path of H, E, B, end. And the rest of this, I'm just going to clear out. And we can now put the critical time for H was 9. So that was the longest path. These are the actual paths, what we call critical paths, because these are the paths that take the most time. Once we identify that time, the most time, we put it in square brackets. We call that the critical time. So the critical time for each task is calculated using a backflow algorithm. This gives us an easier way to do this. So I already said that end takes 0 time. And now we work our way backwards. We take 0 and we add it to 2. 0 plus 2 is 2. We take 2, we add it to 7. 7 plus 2 is 9. And this gives us a very easy way to calculate critical times. However, I can't go back to G because I see G has two different arcs feeding into it. That means before I can determine what G's critical time is, I need to determine what vertex E critical time is. So let's start back at end. And the 0, add it to the 3 for the B. B has a critical time of 3. Let's continue working backwards. It's why it's called the backflow algorithm. So from 3, if we add the critical time of 3 to 5, we get a critical time of 8. And now we have to make a decision here. For vertex G, are we going to use the 9 or are we going to use the 8? Remember, critical time wants to know what is going to cause the biggest delays. So we choose the 9. 9 plus 2 gives us a critical time of 11. So let's clear all of this out. So now let's continue working with the rest of our vertices. I'm going to take the 0 from end and add it to the 4 on C. That gives us a critical time of 4. And now I can take the 4 from C and add it to the 3 from F. That gives us a critical time of 7. And when we get to H, we see once again we have a choice to make. Which critical time are we going to add to H? Well, we have a choice between 8 or 7. We always choose the larger because we want to know what is going to be our delay. So we're going to add a critical time of 8 to H's 1. So H now takes 9 units of time. That's the longest path from H to get to the end vertex. Now that I just want to fix this. This is an 11. Now that we have all these critical times, we can say which critical time should we put by the start vertex. That critical time is 11. That's the largest one connected to start. We saw there were two different arcs feeding back into it. And this tells us that this project can never be completed in less than 11 units of time, no matter how many workers we get on it. And that's because of the chain of events that must take place. In past presentations and in classroom lessons, we've talked about the example of building a house. I can't call in the roofers if the foundation isn't done and the house frame isn't up. that has to be completed before the roofers can be called in. So there's always going to be a minimum amount of time that has to go by for previous steps. And that's the significance of this number. We know that this project can never be completed in less than 11 units of time. So, just to recap, the critical time algorithm is a scheduling process that generates a priority list based on the critical times in descending order. We're going to do that next. The critical time is denoted by a set of square brackets on the digraph. For example, if I had a task Z, the parentheses tells me task time. That's how long it takes to complete that individual task. And the square brackets tells me critical time. That is the chain of events from task Z all the way to the end of the project, and that is the longest path from Z to end. So the notation shown above lists a task Z with a processing time of 5 and a critical time of 13. This means that the task Z takes 5 units of time to complete and a minimum of 13 units of time to get to the end of the project. The word minimum is used because 13 is the best case scenario. That means 13 units of uninterrupted time. However, scheduling projects means juggling and reassigning your workers to obtain the optimal result, which the number of workers on hand. A final note, the critical time for the start vertex is the minimum amount of time in which the project can be completed. If you complete it faster than this, then you likely scheduled a task before one of the precedent tasks were completed, and therefore you have an invalid timeline. So you have to go back and check your work. Let's continue with this example. We've already got the critical times listed in this column, and we want to write the priority list using the critical times. So just like the decreasing time algorithm, the critical time algorithm uses decreasing critical times. So we start with a critical time of 11. That means the first task we want to schedule is G. We have to remember to use the task time of 2 when we put it on the schedule, not 11. 11 is telling us how long it takes to get to the end of the project, and it's telling us to schedule G first, but we must use the task time with G, not the critical time, when we put it on the schedule timeline. Next, after 11 comes 9, but I see I have 2 instances of 9, so we will follow suit with when we have a tie, we use alphabetical order. So we're going to put task D with its 7 units of task time, followed by task H with its 1 unit of task time. The next critical time is 8. That's task E with 5 units of task time. Then we go to 7, task F with 3 units of task time. Next after 7 comes 4. So C4, B3, and A2. So that is our priority list, and that is the priority list that was made using critical times. Now let's create the schedule. So we have our priority list typed out here, and we're going to follow that priority list as we put everything onto the schedule. So just as we've done in the past, we say, can we schedule G2 first? And we say, yes, it's right here, connected to the start vertex. I can schedule it right away. So G takes 2 units of time. That's done. Next is D. I see I can't do D until G is finished. I'm looking for something to schedule at time 0 for the second worker. So I skip over this and look at H. I say, can I schedule H right away? Yes, we can. It's connected to start. That's 1 unit of time. H is done. Now I go back. I say, at Time 1, I'm looking for something to give worker number 2. Can I give them task D? The answer is no, because task D can't start until G is done. G is not done until time 2. I cannot start that at time 1 then. So we're not doing D now. Let's skip over to the next one. Can we do E? E needs both G and H to be completed. Well, at time 1, H is completed, but G is not. I cannot do E. I'm going to skip over E. Can we do F? F requires that H be completed. H is completed, so I can schedule F. I'm going to underline it saying that I'm putting it on the schedule. And since it's 3 units of time, 1, 2, 3, put an F in there. 1 plus 3 brings us to 4. And now I go back to the beginning of my priority list and I say, can I schedule D now? Well, D has been waiting for G to finish. G is finished at this time, so I can schedule it. D requires 7 units of time. 1, 2, 3, 4, 5, 6, 7. So task D will take up this part of the schedule. 2 plus 7 brings us to the 9th unit of time. I'm going to underline it saying it's been put on the schedule. Next on my list is E. E is waiting for G to finish. It's finished at this point. I'm looking at hour 4 or unit of time 4, and that's at the end of F. G is completed at that time. The other thing that E is waiting for is H. H was completed way earlier. Since they're both completed, I can schedule E here. E is 5 units of time. 4 plus 5 brings us to 9. E is scheduled. Now I'm going to look at C next. Both processors finish at the 9th unit of time, so both are available. And I'm going to say, can I schedule C at that time? And C on our digraph is waiting for F. F is done way back at hour 4, so yes, I can schedule C. 1, 2, 3, 4 units of time. 9 plus 4 brings us to 13. I can say that's been scheduled. Now I look at B. B is waiting on E. E is done at the 9th hour. I can schedule that. 1, 2, 3. 9 plus 3 is 12. B has been scheduled. And now A is waiting for D. D was completed back at the 9th unit of time. A is 2 units. That brings us to 13, 14. So this project is finished at the 14th unit of time. And this is 1 block of idle time. So we can say the finish time is 14 and the idle time is 1. Notice how well everything fit on the schedule. The critical time algorithm takes into account the linked events, and that's why we have this new number. G was the longest event to get to the end, so that's why G was scheduled first. H was the second longest, D was third, and that's why D and H are here. Actually, they were tied both with 9. We had to keep skipping over D until its prerequisites were met, but then we scheduled it as soon as possible, and we got all of the what's called the chain reaction of events scheduled to avoid a lot of time waiting and doing nothing where our processors are at idle. So we see it, we got a very efficient schedule here, and everything fit nicely. So let's look at this next example. The first one was your guided notes example. This is your first practice example. Pause the video here. See if you can do this on your own. Your goal is to find each critical time, fill in the chart, and then write your priority list. Once you've done that, unpause the video, and I'm going to advance to the next slide where all of these answers are already in. So here we are. This is the list of critical times in the table and on the chart. And based on those critical times, the priority list is written out here. And now we're ready to go to the next step. So you can pause at this point and see if you can finish the timeline below on your own. I found that this timeline is going to require that I count each box as 2 units of time, so it'll fit in what's printed out here. And then if each one is 2 units of time, that means I would use a half for 1 unit of time. So again, if you want, pause here and try to do the timeline on your own, and then unpause it to watch the solution. So based on my priority list, the first task I want to schedule is B. B is 8 units of time. I'm using these boxes to count as 2 each. So it's 2, 4, 6, 8. And I'll put B in there. I'll cross it off the list. Next is D. That also is connected to start. I can schedule that right away. 2 units of time. Put D there. Cross it off the list. Next is A. A is 13 units of time. It is only waiting for B to be completed. Since B is completed at 8, I cannot schedule A at 2. So I'm going to skip over A for now because my second worker is looking for something to do while worker 1 is still completing task B. So we look at C. C needs B and D to be completed. D is completed, but B is still in process. It won't be done for a while. So we skip over that and look at E. E is waiting for D to be completed. It is done. There's nothing else that E needs, so we can schedule that. It's 15 units of time. 2, 4, 6, 8, 10, 12, 14, and a half a box brings us to 15. And 15 units of time plus 2 means that this is the 17th unit of time in the project. And that was task E. I'll cross that off. Now, as always, we go back to the prerequisite tasks to say, can we schedule them? So I'm looking to schedule A, and we see that the worker that is available is worker 1 at the end of task B. And if we look at this graph, yes, A can be done as soon as B is done. So we're going to take A's 13 units, 2, 4, 6, 8, 10, 12, 13. 13 plus 8 brings us to 21. There's task A. I'll cross it off. Next on the list is task C. C needs tasks B and D to be done. At the 17th unit of time, B and D are both completed. B completed at the 8th unit and D at the 2nd. So I can schedule C. It's 11 units of time. I have 1 unit here, and then 2, 4, 6, 8, 10. 1 plus 10 gives us 11 units. We're at the 28th unit of time in the project. That's task C. I can cross it off. Next in my list is G. G is waiting for C to finish, but worker 1 is ready to go while C is still in process. So I skip over G and I look at F. F is waiting for A to finish. Well, A finishes right here with worker 1, so I can schedule F right away. So those 6 units of time, 6 plus 21 is 27. So my schedule will bring me out to here with F. And I can't start G until C is done. So this is going to be idle time here. And once C is complete, we can schedule G. G is 7 units of time. 2, 4, 6, 7. Remember, this line is the 28th unit of time. 28 plus 7 is 35. And then that gives us idle time down here for the second worker. So we can say that finish time is 35. F for finish time equals 35. And idle time, I have this small block of time here, which was 1 unit, and then this large block of time here, which was 7. So that's 8 units of idle time. So in this next example, we want to complete the project timeline using the decreasing time algorithm first, and then the same project with the critical time algorithm, and we're going to compare the results. So in this first one, We want to make the priority list. So we can write that out. All we're looking at with the decreasing time algorithm, and that's what we're using right here. So based on the decreasing time algorithm, we have task B, which is 9 units. That's the longest. Then E, which is 7. I'm going to fix my 9, make sure it's legible there. After E, we have G, which is 5 units. Then D, 4 units. A, 3 units. C is 3 units. And F is 2 units. So this should fit on the timeline, counting them as 1 unit per box. We start by looking at B, and we see that B is out here. It can't be started. It has prerequisite tasks. Next, we look at E, and we see that E is connected to start. I can schedule that right away. This is time 0, 1, 2, 3, 4, 5, 6, 7. And task E has been scheduled. We go back and we say, can we do B yet? No, B is waiting on A and D. So we skip B. We've done E already. We look at G. Can I schedule G? And the answer is no, it's waiting for F. Can we schedule D right away? Yes, it's connected to start. We're going to put D on the project timeline for the second worker. It is 4 units of time. 1, 2, 3, 4. Put a D in there. That's been scheduled. We go back to the beginning. Can we schedule task B? Well, no, D is done, but it's still waiting for A, so we can't do task B yet. We skip over and we say, can we do G? No, G is still waiting for F. We skip and we say, can we do task A? And we say, yes, well, task A is connected to start. We can schedule that. D was 4 units. A is 3. That brings us to 7. And we can say we've scheduled task A. And now we go back to the beginning and we say, can we schedule task B yet? B is waiting for A and D to complete. At the 7th unit of time, both A and D are complete. So we can schedule B. B is 9 units. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is B. 9 plus 7 brings us to the 16th unit of time, and B has been scheduled. Next in our list is G. G is still waiting on F, so we skip it. After that, the next available task is C. C cannot begin until B is finished. So B doesn't finish till the 16th unit of time. We're looking for something to hand to worker 2 at the 7th unit of time. So we go on to F. F is 2 units. That brings us to 9th. Worker 2 is done and waiting for more work, while worker 1 is still working on B. So we go back, we say, can we schedule G now? Well, G was waiting on F. We just finished F. So let's add G to the timeline. It's 5 units. 1, 2, 3, 4, 5. Here's our G. 5 plus 9 brings us to 14. C cannot begin until B finishes. So this is going to be idle time here. Once task B finishes, we can schedule task C 1, 2, 3 units. It doesn't matter if C is on the bottom or the top of this for worker 1 or worker 2. I'm just being a nice boss, and since worker 1 hasn't had a break, I'm going to let them be able to take a break for the rest of the project. Now that we've done this, we see that the whole project takes 19 units of time, so the finish time is 19. And if we look at this, the idle time, we had 3 units of idle time for worker 1, 2 units of idle time for worker 2. So the idle time is equal to 5. Now we're going to do this same exact project over, but this time we're going to use the critical time algorithm. The critical time algorithm, we're hoping, will beat this finish time of 19 and be more efficient, because critical time takes the chain of events into account. So here we have uh, our same graph. We have to now find the critical times for each vertex. So the end vertex has a critical time of 0. We'll use the backflow algorithm to find critical times for each vertex. I added 0 to the 2 vertices connected to end, and then we continue to work backwards. I can add C, which has a critical time of 3, to 9. 9 plus 3 gives B a critical time of 12. I can take the critical time of 5 on task G and add it to task F. So 2 plus 5 gives F a critical time of 7. And I see that task D has 2 arcs feeding back into it. So I need to choose which critical time do I add to task D. And we see I have to add the larger. So 12 plus 4 gives D a critical time of 16. 12 plus 3 on A gives A a critical time of 15. And E is 7 plus a critical time of 7, so that's 14. And now that we have all the critical times, we can make our priority list in order of decreasing critical times. The longest critical time is 16, so that's the project's fastest time that it can be done in. If you recall, I'm going to go back a slide, we did the project with 19 units of time using the decreasing time algorithm. Now, let's see if we can beat that. We see we have the potential to beat it because 16 tells us that it could potentially complete the project in 16 units of time. That is the critical path from start to end. All right, so let's schedule these. Let's make our list. First task is D. Remember, we use the task time, not the critical time, when we're scheduling. So the priority list starts with a D4, then comes A3, E7, can't read that 3, all right, that's 16, 15, 14, next comes 12, so B9, F2, you go down to the next line, G5, and C3. So the critical time algorithm tells us that we should schedule these tasks in this order to take into account the chain of events that slow down projects. So let's see how this goes. First is D. Can we schedule that right away? Yes, it's connected to start. And that's something else we should notice, is that the vertices connected to start will have the largest critical times, so they will often be at the beginning of our priority list. So that means that we should usually be able to schedule our initial tasks in the list. So D takes 4 units of time. We're starting from 0, 1, 2, 3, 4. There's D. Cross that off the list. Let's do the schedule in blue. I have enough red ink here. Next task in the list is A. A is connected to start. It's 3 units of time. 1, 2, 3. Can cross A off the list. Next task in the list is E. That is also connected to start. So I can do that. As soon as A finishes, I can schedule E. It is 7 units of time. Seven units plus 3 brings us to 10. Cross that off the list. Next is B. B is waiting for A and D to finish. Well, A and D are both finished at this time, so I can schedule B. B is 9 units of time. 9 plus 4 is 13. Scheduled. Next in the list is F. F needs D and E to be complete. At the 10th unit of time, E completes and D completes back at 4. So we say, yes, we can schedule F. It's only 2 units. So that brings us to 12. Cross it off the list. Next comes G. G is waiting for F. Well, we just finished F. That's 5 units of time. 5 plus 12 is 17. Off the list. C is waiting for B. B finished back at 13. 1, 2, 3. That brings us to 16. And then 1 unit of idle time. And we see that the finish time here is 17. And the idle time is 1 unit. And we say, yes, we have completed the same exact project more efficiently. And that is why project timelines are helpful in finding ways to avoid downtime with our workers, or if we're talking about bigger projects, um, if we have to rent a couple of cranes on a job site, we don't want to rent them if they're not going to be used. We don't want them sitting around idle. If we go back to the previous slide, we saw that we had 5 units of downtime. In terms of big projects, that could be 5 days, 5 weeks, 5 months. We don't want to incur those costs. So if we can bring the downtime down to 1 or to 0, we've made a very efficient schedule and we have less waste in our cost and time to complete the project. So that's the end of this presentation. Again, go back, watch the video, read your notes, and do the homework practice. Check the answer key. Send me questions if you have them. We can always meet in a video chat. And then I'm also uploading a quiz online based on critical time algorithms.